In this video, we are going to be discussing how to solve a system of linear equations using substitution. Our goal in order to use substitution is to have a variable, x or y, completely by itself on one side of the equal sign. For example, if you have y equals and then 2x plus 6, y is all by itself on one side of the equal sign. If I had 4x minus 3 equals y, you can see y is the only thing on the right-hand side of the equal sign. The same goes for x. If it says x equals 2y minus 7, x is completely by itself on one side of the equal sign. And the same would be if we had something like 5y minus 1 equals x. We have an x completely by itself on one side of the equal sign. One of the equations has to have this be true in order to use substitution. So we can see in this first example, we have a y that is completely by itself here. So I'm going to circle this y. The equation is telling me that y is equal to negative 2x minus 9. Since we circled the y, I like to put parentheses around the y in the second equation. That helps remind me that instead of writing y, I'm going to replace it with everything I highlighted in yellow. So I will rewrite my bottom equation, and instead of putting y here in the parentheses, I'm going to replace it with negative 2x minus 9. A good method to make sure that you did this correctly, or a checkpoint, is to ensure that once you do your substitution, all of your variables are the same. So when I look at this line that I just rewrote, I should see only x's as my variables, or sometimes it's only y's as my variables. From here, I just have a multi-step equation that I can solve. So I distribute to get 10x plus 45 equals negative 19. I see two terms that both have x in them, so I'm going to combine like terms. And then I'm going to subtract 45. So 16x equals negative 64. And divide by 16. X is negative 4. This is only one part of the ordered pair that we need. We need an x and a y coordinate. So I'm going to take negative 4, and I'm going to go back to the equation that I originally had isolated. You can put negative 4 back into either equation, but it's easier to substitute it back into the equation that had the isolated variable. So y equals negative 2. Instead of an x here, I'm going to replace the x with negative 4, and we will simplify. 8 minus 9 is negative 1. This means negative 4, negative 1 is the solution to this system. So these lines intersect at negative 4 and negative 1. Let's go to another example. Remember, I'm looking for x on its own on one side of the equal sign, or y on its own, or x or y on the right-hand side on its own. So when I go to circle a variable, x is not by itself, so this equation won't work. Y here has a 6 attached to it, not by itself, won't work. X here is not by itself, y here is also not by itself. In order to use substitution, we can force one of the equations to have an x or y completely by itself in order to substitute. So if you look carefully at the top equation, it looks like we can get this x by itself pretty easily if we just subtract 7. So my new top equation would be 6y minus 7. Now I have an x term by itself that I can rewrite my bottom equation, and instead of an x, I'm going to be replacing it with 6y minus 7. So 4 times 6y minus 7 plus y equals negative 3. I'm going to distribute. I get 24y minus 28 plus y equals negative 3. We have y terms that can be combined, so 24 and 1y would be 25y. They combine on the same side. Add 28. So 25y equals 25. Divide by 25. We get y is 1. Now again, you can go back to any equation and substitute 1 back in for y. It doesn't matter which equation you choose. You could put it back into the top equation here before we manipulated it to be 6y minus 7. You could put it into the bottom equation. I just like to go back to the one that I originally had circled for substitution. So 6 times 1 minus 7. Notice I just took, since I know y is 1, this y here I replaced with a 1. So 6 minus 7 is negative 1. That means the solution to the system is negative 1 comma 1. That is the point at which the lines intersect. I also want to take a minute to cover the special cases that we could see with substitution. So here you can see that y is by itself, which means I'm going to replace y with everything that I have highlighted here. If I do that, I would get 12x minus 6 times, in the parentheses, I'm putting 2x plus 1. That's what y was equal to. If I distribute, I'll go to combine like terms and notice that these terms, 12x minus 12x is 0. So negative 6 equals 5. When the variables eliminate and we get something that is not true, that means that this system has no solution. Recall that graphically, that means if I were to put both of these lines on a graph, they would never intersect. They would be parallel lines. Now, if we do the same procedure, so this is the same question, I'm going to set it up the same way, I just changed one number. We would replace y with 2x plus 1. So I get 12x minus 6. And then in parentheses again, I'm going to put 2x plus 1. Now here, if I distribute, again, I'll notice that if I go to combine like terms, my 12x's make 0. They subtract out. But I get negative 6 equals negative 6. If your variables eliminate and you get a statement that is true, that means that this system has infinitely many solutions, meaning that these lines are actually exactly the same line. They would be graphed one on top of the other and intersect in infinitely many places. So if the variables eliminate and we get something that's not true, no solution. If variables eliminate and we get something that is true, infinitely many solutions.